Okay. So, however far you got is fine. We've got some time constraints here that we've got to cut you off. You know, anytime you do something like this, like I could have just stood up here and like told you what was up, but I didn't want that to happen. But you know, because of that, you know, I want to give you some time to work through here. But ultimately, you know, we got to put an end to like your work through. All right. So listen, what we're about to do now is use what you just did as a vehicle to learn new stuff. So, and this is tough sometimes for kids to grasp. I am teaching you new stuff. How would most or many teachers do it? And how do I do it sometimes? You walk in the room, you sit down at your desk, you take out your notebook, and we learn new stuff. So therefore, when it ends up in this type of setting, sometimes people don't grasp that we're learning new stuff. And they don't do the things that they would do if they walked into the room and they sat down at their desk and said, we're learning new stuff. So whatever you would normally do when you're learning new stuff is what you have to do right now. You can stay in your group if you want. You can go back to your desk, whatever it is. Some people don't like to write stuff down. So most people do, right? But simply because we got you up and doing stuff and I'm now talking doesn't mean this isn't new stuff. And that's tough sometimes for people to grasp and to get. Okay, so we are about ready to learn new stuff, and Maddie Farrader is going to teach us the early part of this lesson by recounting our exchange early in the class. So you called me over, Maddie, you had a problem.
Yeah.
Okay, what was the problem, Maddie?
I thought our slope was like way too big because we had like 25x and negative 17.3x.
Can you do me a favor and give me those two equations, Maddie?
Yeah. One was 25x plus negative 26.
Plus negative 26?
Yeah.
Okay. And what's the other one?
Negative 17.3x plus 117.
Plus 117?
Yep.
Okay. And that would be equivalent to, so like this one would be equivalent to my red line. Okay. It's not the exact, it's not my red line, right? How do we know it's not my red line? Yeah, what specifically, Owen, that you can maybe see right off the get-go?
She has a starting point of minus 26.
Yeah, her initial location, right, is at negative 26. Mine's at like negative 0.1, right? But why do we know that this is the red line, Owen?
Because the slope is increasing, it's positive.
Awesome, slope is positive, blue slope is negative, okay?
Did you want the other equation from
This is totally fine,
Okay.
okay? All right, so Maddie, what was the problem?
I thought that it was too big because I didn't think it made sense. I thought it was supposed to be like a decimal, like.
So these slopes, I must have done something wrong, Mr. Smith, because these slopes are too big. And what was our conversation, Maddie?
The slopes are actually the centimeters traveled per second, which is the speed. And it does make sense because we tested it out with the car on the ground, and we said that in about 4 seconds the car should go 20, no, sorry. In the 4 seconds the car should make it all the way across, or 100, and I'm really bad at science.
Oh, you're all right, you're doing fine.
And that was the speed, so it was correct. By using like an actual real life example, we were able to see that it was correct.
Perfect. Listen, the first thing we want to address is making an assumption that something is wrong without the knowledge of like what it was. All right? Don't discredit what your work is because you have some random reason for thinking that it's off. Oh, our slopes for the last two graphs were decimals. or were small. Therefore, these graphs' slopes should be small. Well, guess what? The very first lab that we did, the slope was pi, because C equals pi times D. C over D is equal to pi. There was a reason the slope was approximately pi. Okay? Then what happened? Then you did a lab about the baseboard moldings, and depending on like what your molding is and what units of measurement you had, somebody's slope came out to be in the like 0.77s. All right? How come? Because what you were measuring was a linear density. So people were measuring grams per unit length. They were measuring the length of their baseboards and then their masses. And guess what? It just so happened that for each centimeter, there was 0.77 grams or something along those lines. All right? And everybody's numbers would have been different because some people did it in inches, some people did their mass in kilograms, and so on and so forth. There was a reason for this number. There's a reason for this number. These two numbers don't have anything to do with this. Here's the major key. We have this new introduction of new terms. Here's our new terms for today, everybody. Speed and velocity. There's our new terms. And what you just did with these graphs essentially brings us to these two ideas. So, Maddie, if you could describe, based on what our interaction was, what speed is, what would you say speed is?
Speed is the amount of distance that something travels in a certain long.
Yes.
Right?
Yes.
Yeah, it's the amount of distance something travels in a certain amount of time.
Perfect. Speed is, I'm going to be a little bit more formal. It is the rate of change of distance. To put it in better words, the words that Maddie just used, it's the amount of distance traveled in a given period of time. We're going to get to this velocity term, but I'm going to erase it for a second. Somebody else. If I had to write an equation based on those words, what would it be? Speed equals what? Drew. Yeah, distance over time. Now, one thing I want to say about speed, and I've said this word, but I just kind of glossed over it. Speed is a scalar quantity. A scalar quantity means direction is not part of it. What type of quantity has a direction associated with it? Vector quantity. The vector counterpart for speed is velocity. So velocity is the vector counterpart for speed. I might be asking you for those equations again in a second, Natty, but I might just use mine too. So velocity is the vector counterpart, let's just say, for speed. Oh, by the way, distance is the vector counterpart for, distance is the scalar counterpart for what vector quantity? Displacement. So these two, they're kind of partners. Speed's a partner with distance. Velocity is a partner for displacement. So guess what velocity is going to be? Velocity equals change in displacement over change in time. And we write that as an equation like that. Displacement or position is x. T is time. We put a bar over here that means average. And we'll talk about that idea next week. You know, and this is perfectly logical. Think about it. 30 miles an hour. That is a distance or a displacement over a time frame. 100 meters per second. Distance over a time frame. If we could ever get into Canada, we'd be driving 120 kilometers per hour. Right? The speed of light is like 186,000 miles a second or something like that. 3 times 10 to the 8 meters per second. Displacement divided by time. So then if I graph displacement on the x-axis and time on the y-axis, what does my slope give me? How do I take the slope? Slope is delta y over delta x, meaning the y-axis and the x-axis. Well, what's my y-axis? Displacement. What's my x-axis? Time. Well, what quantity is the change in displacement over the change in time? Velocity. In big, giant letters in your notebook someplace if you would need our writing stuff. The slope of a position versus time graph is velocity. All right, so Jolie, you look at this graph. Blue line, red line. What's the one thing that probably pops right out to you that's different than the blue line and the red line? What's the major difference? What's the major difference in their slopes? Yeah, which one's got a positive slope? Which one of these has a positive slope? Yeah, the blue one's got a negative. If slope tells us velocity, what do the plus and minus mean on a vector quantity? Ooh, who said that? Maddie, what does it mean? Yeah, didn't we talk about this? Negative displacement is this way, which means positive displacement is this way, right? We went out there and we had some people moving along those yard lines. Somebody went in one direction, a positive displacement. Somebody goes in the other direction, that's a negative displacement. This is a positive velocity because it's a positive slope. This is a negative velocity because it's a negative slope. Andrew, someone moves 100 meters in 10 seconds. What's their velocity? 10 what? 10 meters per second. Jack, somebody goes 200 miles in 2 hours. What's their velocity? Per hour. This velocity is always a ratio. Now, how can we get velocity? Well, if we're given 2 numbers, we can just divide those 2 numbers. If we're given a graph of position versus time, how do we get the velocity? Take the slope. It is the rate of change of position or displacement. This is our rate of change of distance. Now, there's a couple of technicalities there. All right? Let's think about this. Right? If I walk 5 meters this way, 5 meters this way, 5 meters this way, and 5 meters this way, How far do I want? 20 meters. Let's just make up some numbers to make it easy. Took 10 seconds. If I move 20 meters in 10 seconds, what's my average speed? 2 meters per second. What's my displacement? 0. So what's my average velocity? Seems weird. It's 0. Why? Because of the straightforward definition of these two numbers. Now, here's what makes, well, lots of things make this course tough. If there's only one version of my path, those two terms often get utilized the same, right? So speed and velocity, if I'm running the 100-meter dash, hey, what's my speed? What's my velocity? The number is going to be the same. Velocity is just going to have a particular direction associated with it. So oftentimes the numbers for these two quantities, speed and velocity, are the same. But velocity would have a direction associated with it. There are, again, some of those odd situations where velocity and displacement, or velocity and speed, are different. All right? Now, last thing here, okay? So, where do these two things collide? Ryan, in general idea or terms, where do these two things collide?
Like for the X value?
No, you don't have to give me a value. Like, describe what you're looking for. If the question is, hey, where do these two things collide?
It's where they're both at at a specific time. So like at 4 seconds, or it's where they're at the same at a specific time.
Where they're at the same what?
Same distance.
Same position. What's that mean for the graph? When they intersect, right here. That's the same position at the same time. It can't be this time because this thing's located down here and this thing's located up here. So in this case, it's like 2.2 seconds and at a location of like a little bit over 1 meter. That's my estimate. All right. Now, my equations of best fit, this thing is minus 1x plus 3.2. This equation is 0.5x minus 0.1. What's the x mean here? What's the x mean? Ooh, Jolie, say it? Yeah, how come? Oh, in reality, in physics terms, here's what this is saying. Ooh, and the terms get mixed up. X stands for position equals minus 1 times t plus 3.2. So we've got to take what the graph is spinning us. Because the computer doesn't know what these x and y values mean. So what's this mean? Well, position equals 0.5t minus 0.1. So how do we find the value of time for this? Well, again, what do we know about the x locations for each of these cars at this particular spot? They're the same. So what do we know about this and this? They're equal. So what can we do about this and this? We can set them equal. So minus 1t plus 3.2 equals 0.5t minus 0.1. Bring this over, and I've got 1.5t equals 3.3. Two is 3, and I think that's 2.2. So the time equals 2.2 in that math. Oh, look at it. There's 2, Is that slightly more than 2? Does this make some sense? Yes. How do I find the location of where they actually collided? Owen,
Plug 2.2 into the equation.
which equation?
Either work.
Perfect. If I plug 2.2 into here, I get the same answer as if I plug 2.2 into here. And that answer is like 1.1, I think, in my number. You would have different numbers. All right, so what have we done today? We've introduced 2 new terms. We've talked about the math equation on how you would calculate the value for those 2 terms. Because, look at that's distance, this is displacement or position over time. There's distance over time. Half the time, they're the same, more than half the time. We've also talked about what that stuff means from a graphical perspective and how you get that off of a graph of position versus time. So we laid the groundwork early in the week with position, distance, and displacement. Now we take our next step to velocity. And then mid next week, we'll take our next step to what's called, so look at, wait a minute. Velocity is a rate of change of displacement. So we have a term for when displacement changes. That term is velocity. There's also a term for when velocity changes. Does anybody know the term for what it means when velocity changes? What do we call it when we change the velocity of something? Zoe, acceleration. And they have similar relationships. So we'll kind of have a next week that's similar to this week, just with different quantities. Okay? Now, you got a 10-question castle learning for the weekend. That 10-question castle learning, all of it should be able to answer with this 15 minutes. Okay? Anybody got any questions?